Hello everyone, I hope you are happy and healthy. Let's continue the discussion about the analog to digital conversion from the optimal voltage range. Well, as I mentioned, the resolution of the analog to digital conversion is the change in the output that causes the digital output to change by 1. Some of the sensors output voltage are not in the range of like VRL minus the VRH, which means we need to use a circuit that shift and a scalar transducer output to improve the accuracy of the A to D conversion. Then it falls in full range of A to D conversion, that is 2 to the power of n minus 1. This is how we can compensate that voltage. Now, which kind of circuit do we need to use? Any idea? Well, it is an op-amp, which you are familiar with it, that we can use to do so. So you said in the first schematic that I show you for the converter. So now, what is an op-amp? Well, it is an integrated circuit that can amplify any weak electric signal. Then it can be like, let's say, called the best analog circuit to match the spans, because it can level shifts or like amplify the input voltage to make the spans. So it means it can simply convert resistance to voltage, right? Now, I can say op-amp in here is a level shifter, as you can see in here. It is a shifter. It can just do the level shifting, or amplifies that it can also subtract or add the reference voltage from the input to compensate for DC offset voltage. Well, if you look at the schematic in here, which is the schematic of an op-amp, it has 2 inputs, right? And 1 output. So generally, you may see VCC in here, right? Or even you can see VDD instead of V plus or V source plus, which is the power supply, which is the voltage from the power supply. So you may see also VEE or VSS, right? Instead of the V minus in here. So what does that mean? These are like the power supply terminals that like we are showing them based on that. So when you use bipolar junction transistor, which is the BJTs, inside of op-amp, the power supply corresponds to the collector and emitter. That's why we call them VCC or VEE. When you are using the field effect transistor, which we call them FET, like inside the op-amp, that's when they label it as VDD or VSS. That's the reason for seeing different labels for these terminals, but these are generally the terminals for the power supply. Now, what you're seeing in here, this is the closed loop circuit. So in here, we wanted to look at how we can calculate the voltage, the output voltage. So the closed loop gain is the gain of the amplifier with the feedback loop closed. So the closed loop gain of the op-amp can be simply calculated using this equation. So it's the ratio of input voltage over the output voltage generally. So the output voltage, right, is going to be a result of the input voltage times like this resistance. Now, let's analyze that in more detail. Although you are expected to be familiar with op-amp operation, and I have also uploaded a quick review about the op-amp operation on Avenue, alongside the solution for the other examples that I solved them during the class time last session. So you may want to go there, review them, but still I'm going to give you a quick review about the op-amp operation to remind you in case you forgot about it. How is the op-amp operation? So, well, let's first draw the schematic, the exact same schematic that in here, we have it in here for the op-amp. So op-amp is going to be something like this. As I mentioned, we are going to have two input, right? Which we call them V positive and negative. And we are going to have one output. Also, these are the power supply terminal, Vs minus and Vs, sorry, this one is positive and this is minus. So generally, any op-amp can have or can include inside it something around 30 to 50 other components. It's not only what you are seeing here. There are a lot of other components inside it. So now, how about the gain? The gain is in the range of, the gain of this op-amp is something in the range of, let's say, 10 to the power of 5 up to 10 to the power of this, 6, which is like the gain of the op-amp. Then if the input is going to a system, if I have a system like this, if I have an input in here, which is the input voltage, and this is going to be my gain, this is going to be my output voltage, then we wanted to see what is the relationship between this input and output. How to do so? So simply you can tell this is going to be the output voltage is going to be A times input voltage, right? It means we have a differential output. So using this, you can say V out is equal to A. Then what is the input voltage? Look at here. The input voltage is positive voltage of the source or the power supply and minus this guy. Now, if I wanted to map this one, how it should be. So it should be something like this. So this is going to be my input, and this is my output voltage, right? What is this gain? This gain is going to be like this, right? What I have in here, which is the positive voltage from the power supply, and this is going to be the negative voltage from the power supply. So this is going to be my gain. Whatever I have in here, this is going to be my A. That's how I can map this equation. Now, what is the closed loop gain of non-inverting op-amp? Right? I'm going to talk about a non-inverting op-amp. So how to do that? How to calculate the gain of a closed loop gain of a non-inverting op-amp. If I have an op-amp, and I'm gonna just kind of draw the equivalent circuits of that op-amp, I can draw it like this. Right? Let's say this is my op-amp. I have the positive and negative input in here. This is going to be V positive. This is going to be V negative, right? And then whatever I have in here is going to be the non-inverting, right? Whatever in here is non-inverting. And whatever in here in the connected to the negative terminal, this is going to be the inverting, right? So now, if I have input voltage going from here, right? And I'm gonna have the output going from here, what will happen? Then in order to create a closed loop op-amp, a closed loop non-inverting op-amp, I need to add a couple of resistors right in here. So I'm going to add one resistor in here and another one in here. This one is going to be connected to ground. So I'm going to call it RG. And this one is going to be my reference. So I'm going to call it RF. Now, where should I apply the voltage? Since I'm gonna create a closed loop op-amp, I'm gonna apply the voltage right in here. So then I'm gonna connect it like this. This is going to be connected to my inverting voltage, which is the negative terminal, right? Now, you know that this is my gain. Here is positive and here is negative. Now, if input voltage is going to the op-amp from here, which is the non-inverting terminal, then I have, like for example, from here, it is going to be the non-inverting terminal, and I have the gain A, and I wanted to see what is the relationship between this input voltage and this output voltage. That's what I am looking for. So the first thing I need to do, I have to draw the equivalent circuit. How to do that? So first thing first, I have to draw my voltage source, which is going to be something similar to this, right? I have already said my output is going to be right in here. And then I have like the same reference resistor and also the ground, the one connected to the ground. And the other end, which is the negative, is going to be also connected to ground. So I'm going to just connect both in here. And then I'm going to ground them, right? Or you may want to draw it this way. So this is my RG and this is my RF. Again, like exactly like this. Where should I apply the voltage? I have to apply the voltage right in here, right? So this is going to be my V in, which is going to can be connected to my negative voltage, which is going to be my negative source, and it is going to this direction. How about my positive force? The positive like voltage source is going to be in here, which is going to be the non-inverting. So this is the inverting, which is connected to my resistors, and this is the non-inverting. Now, if I apply current to the circuit, right? If I apply current to here and here, what will happen? Then these two currents are going to be equal, which means, right, I positive is equal to I negative, which is 0, which is almost 0. Then what should be the output? If the current is 0, then the output is going to be Again, same thing, exactly what I have in here. That's how I can find that equation. And this is positive, this is negative. So using this, now I can find the negative voltage is equal to V out times, if I just substitute like the resistors, which is going to be R G over the RF plus RG, right? This is how I substitute this negative voltage, right, in here. So now if I have this one for the voltage, I can simply put this one in here and calculate the output voltage, which is going to be A, and then if I substitute this one in here, it's going to be V in right, divided by 1 plus A RG over RF plus RG. So before I do this one, maybe it was better to just write this way. So in here, V out, if you don't know how I found that one, V out is A times V positive minus, I'm gonna put this one in there, V out RG over RF plus RG. Then what I did, it was in here, since we are connected to the non-inverting terminal, which is this guy, what I did, I assumed that V positive is going to be equal to V in, right? That's why I rearranged the equation like this. So from here, I have V out equal to A times this term. And then if I replace that one or substitute that one, this is how I can rearrange the equation. And if A is a large value, let's say in here, if A is going to infinite, what will happen? Then I can rearrange the equation like this. I can have it like V out equal to 1 plus RF like over RG times the V in. And this is exactly what I was looking for. I was looking to find a relationship between the input and output voltage. So I'm going to have the gain go to infinity, and then I can simply find a relationship between the input and output voltage. What do I call it? Now I call this one the closed loop gain of non-inverting op-amp. This is how I can calculate the closed loop gain of non-inverting op-amp. Now, using what I explained, you can find the V out for other typical op-amp circuits, such as a summing circuit, like what you are seeing in here, which multiple inputs are connected, as you can see, to here, are connected to the inverting input terminal of the op-amp, and also to the non-inverting terminal of the op-amp. And also you can look at the non-inverting input terminal, which is connected in this case to the ground, right? And because of the configuration of this, the output of the voltage is like an adder circuit, so which is out of phase by 180 degrees with respect to the input. That's why we have it like this. Or there is another one in here, which we call it the voltage follower, which is known as a buffer amplifier. So this is also having a unity gain amplifier. In this op-amp circuit, the output voltage is equal to the input voltage, right? The output is equal to the input. And that's why we call it the output is following the input, because these two are like this is V out, and these are equal, as the name shows. And it doesn't amplify the input signal. Also, it has a voltage gain of 1. So you use the same resistor connected to here and here. That's why those two are almost equal. Well, there is another case in here, which we call it the shifter amplifier or level shifter, a scalar circuit. So this is the level shifter amplifier that add or subtract a known voltage from the input to compensate for DC offset voltage. I already explained about this. And you know it that op-amp have level shifter. I have already said there are some level shifter inside the op-amp. So in this design, how you can calculate the output and input relationship, this is going to be something like this, right? So in this case, this is the like a scalar, what you are seeing in here. You scale the input voltage with 2 resistors, which is like this resistors in here. And also this one will shift it, right? So this is about the scalar and this is about the shifter. So this term will scale, this term will do the shifting. Now, explaining this, let me just solve some example for you to make it more clear. What are these equations and how we can use them in order to find out what is the best analog to digital converter for like our application. In the first example, you are asked to design the required circuit and choose the appropriate value to scale this range, right? To scale the 0 to 200 millivolts, 0 volt to 200 millivolt to 0 to 5 volts for the analog to digital converter. This is what we are going to do. So now how to do it? We need to use non-inverting amplifier, right? What we need to do, we need to use non-inverting amplifier to amplify the voltage for efficient use of A to D. So the scaling can be, we have already explained this one, how we can calculate the scaling. The scaling can be calculated using the scaling equation, which is the relationship between the output over input. That's how we are going to calculate the scaling. So this is going to be example 3. I'm gonna start it from here. I have already uploaded the solution for this example, but I'm gonna solve it in here for you. So what is the voltage? It is going to be 0 volt to 200 millivolts, and I'm gonna just scale it to the range of 0 to 5 volt. This is what I am going to do. So as I mentioned, for a scaling, I have the output voltage over the input voltage. In this case, what is the output? It is 5. And what is the input? Input is 200 millivolts. So if I convert it to volt, it is going to be something like this. So from here, I have simply like 25. What does that mean? It means the transducer voltage must be amplified 25 times. right? It must be amplified 25 times. Now, from what we discussed earlier, you can find the non-inverting amplifier resistor. So how to do it? Remember I said we have the equation which is V out equal to V in 1 plus R2 over R1, right? Let me first bring you a picture, which is just making it much easier for you to understand. Let's say this is the picture. This is exactly what I draw in the previous slide. So this is my R2, this is my R1, this is what I am talking about. Now, from this one, I said I am going to have like V out from the previous one over V in to find the scaling. And I have already calculated that one, which is going to be 25 times. So I'm gonna just rearrange the equation and substitute this one, which is going to be the V out over V in, which equals to 1 plus R2 over R1. Now I have this one from the previous calculation equal to 25 times. So from here, I can tell R2 over R1, if I just send this one to the other side, is gonna be 24. So what does that mean? From here, I can calculate my R2 and R1 relationship, which means R2 is equal to 24 R1, right? R2 is equal to 24 R1. It means I can use any resistor with the ratio of 24, right? Any resistor with the ratio of 24 to provide the 25 times amplification, because I need 25 times amplification. For example, I can use R1 like 10 kilo. Let's say if R1 is like 10 kilo, right? Then how much is the R2? Then from here, you can simply say R2 is 240 kilo. This is just as an example. So this is how you can find out which kind of resistors you can use to create your closed loop, right? Your closed loop op-amp. Now there is another example in here that wants you to design the required coordinating system. Look at here. You have example 4, and you are asked to suppose the transducer output voltage range from -1 to -1.2 volt to 3 volts. And then you are asked to design the required circuit and choose the appropriate value to scale this range from here to again 0 to 5 volt for the analog to digital converter. So this is somehow similar. So what I am going to do, this is going to be example 4. Right? We need to again, this time, use the shifter. Let me go back to this slide. This is the shifter, right? We are going to shift it. So we need to use the shifter and a scalar circuit for efficient use of analog to digital. So the voltage from -1.2 volt to 3 volts must be mapped to what it was asking here, 0 to 5 volt. So let me bring that exact circuit from the previous slide to again make it much easier for you to understand what I am doing. So I'm gonna take this picture, bring it here. So I'm gonna use the shifter and a scalar circuit. So the voltage from, this is the range of the voltage that I am going to convert this time, minus 1.2 volts to 3 volts. And I'm gonna map it to 0 to 5 volts. Now, look at here. R0 is used for inverting the voltage, and it can be any value, right? Because this is connected to the inverting terminal. But R1 and also R2 and RF, these three, right? We need to calculate them. So R0 can be any value, since they are used for inverting the voltage, but I have to calculate this. So we can use the lowest and highest value point because the transducer voltage changes linearly, like what I showed you in the previous slide. So it can change linearly versus the desired analog to digital value range. So now, what is the lower voltage? First, I'm gonna go over the lower voltage. So for the lower voltage, if I have the input voltage equal to minus 1.2 from the problem, right? And also the analog to digital voltage, the analog to digital voltage, which is V out, is going to be 0. So what do I have in here? From this, I can tell the V out is equal to RF, which is this one, over R1 times input voltage, right? Minus RF over R2 times V1, right? So what do I have in here? I have already this one equal to 0. So I'm gonna just rearrange it. This is going to be 0. And I'm gonna have this term, which is RF over R1. And then V in is already given. It is given as 1.2. So I'm gonna substitute that number, right? Minus, I'm gonna repeat this term because I don't have them yet, over R2, and V1 also is not given, so I'm gonna just leave it as V1. Now, from this equation, you can simply say that V1 is going to be a negative number. If you just rearrange this equation, this one is going to be a negative value, right? So what can we do then? Now, first let's draw the other equation, which is going to be the highest voltage. How about the highest voltage? For the highest voltage, this is the lowest, highest is 3 volts. Then I have the input equal to 3 volts, right? And I have the V out, the analog to digital V out equal to 5, right? These are from the problem. So what do I have in here? I have the V out RF over R1, V in minus RF over R1, again V1, same thing. Now, if I just substitute the number, this time my V out is 5, so I'm gonna just put it as 5. It's gonna be, again, I'm gonna repeat RF over R1, but my input this time is 3 minus RF over R1, and V1 is again something that I don't have it. So I'm gonna call this one equation 2, let's say, and I'm gonna call this one equation 1, and this is going to be equation 2, right? Now, we can find R1, R2, and RF using these two equations. How to do so? So, as I mentioned in here, V1 in here must be something negative, right? Since the value of resistance are always positive, we cannot have this one like negative, then they can be infinite number of solution for R1 and R2 and RF, right? But we know that all resistance always should be positive. So what we can do is we can select -5, right? For V1, like this. And then we replace like the equation 1 with the -5. We are going to substitute the V1 by -5. Then what do we have in here? From the equation 1, we have like 0 RF over R1 minus 1.2 minus RF over R1, and I'm gonna just rearrange it. So my V1 is going to be -5. How about the equation 2? From equation 2, I have same thing, 5 RF R1, then I have 3, and then I have RF over R1, and again, I'm gonna have my V1 equal to -5. Now using this two, if I just have some assumption, for example, I'm gonna assume this term is going to be equal to X1, right? And RF over like R2, this is R2, this one is going to be X2. Also, this one is R2. So all of this are R2, sorry for the typo in here. So then if I do so, I'm going to have X1 equal to RF over R1, and I have X2 RF over R2. Now, if I just rearrange those equations, the previous one, what do I have? Then I have -1.2 X1 plus 5 X2 is equal to 0. And for the second equation in here, I have 3x1 plus 5x. I'm just replacing this because this one times this one is going to be positive. That's why I have 5x2. Then this is going to be equal to 5, like what I have in here. So now, if I again rearrange it, what do I have in here? I'm going to have 4.2x1 equal to 5. From here, I can find out what x1 is. x1 is going to be 1.2. And then from this, R1 is going to be RF over 1.2, right? So if RF is 12, then R1 is 10, right? As an example, if I have, let's say, RF equal to 12, right? then what is R1? R1 is going to be 10 kilo ohm. So we can replace X1 now in equation 1. And then what do we have? If I put the like X1 in this equation, or maybe even this one, I will get this. I will get the X2. So far I found the X1. Now I need to find the X2. To find the X2, I have to put the X1 from here to here. So I'm gonna have it like X2 is equal to 24 X1 from here. X2 is 288. And I can find the R2. What is R2? It is, look at here, RF over X2, which is going to be 0.288. And it is, if you just use your calculator and put the RF, which you have it already 12 in here, it's gonna be 42 kilo, right? So now I'm gonna leave this example in here for you. There's another one. So there's another example, which is example 5, since we have already discussed example like what you see in here. Example 3 and 4. I'm going to leave the example 5 for you to practice because we have already finished this. But still, the result or the final solution of the example 5 is uploaded on Avenue. You can just go ahead later, even check that one as well after you solved it yourself. Now, remember I said we are going to create an analog voltage from samples. So that is why we call this process analog signal reconstruction, as you can see in here. So in this process, a digital to analog converter takes a series of binary numbers and then recreates the voltage level that corresponds to that binary number. Then the signal is filtered by a low-pass filter. So that's how the process is going to be completed for a conversion. So it is shown in here like as sampling. So the first one is the analog input. It's going to be sampled at some frequency. And then whatever we have in here is the captured digital input. So look at this picture. If I'm going to map this one, and if this is going to be my V like T, and this is going to be my like T of S, let's say in here, and this is going to be my time, right, in second. This is my voltage, and this is my time. What is going to happen in here? From here to here is the sampling interval. You are familiar with this. We call it TS. What is TS? I explained this. TS is a function of frequency, 1 over frequency. So what do we call this one? We call it sampling interval or sampling time. So it means there is one sample in here, there is one sample. It means this time is the time that is the like difference between this sample and this sample. And the frequency that you are seeing in here, this is the sampling rate for the frequency, right? We call it Fs, that's the sampling rate. So this one is also per second, which is the number of samples per second. This guy in here is number of samples, as I mentioned, per second. Now, if a sinusoidal signal is sampled with a high sampling rate, which means a higher frequency, something like 2F or more, the original signal that you are seeing in here can be captured in a way that we can find out how is the trend of that signal, right? But if it is going to be sampled in a lower frequency like this case or this case, since we have less number of sampling, it doesn't give us any understanding about how is the analog input, right? So in this case, as you can see, it is going to give me something like a straight line, right? This is a straight line. It doesn't, this line is not giving me any information about how is the sinusoidal wave. So as I mentioned, this is the sampling time, but for the first case, how about here? Look at here, in this case, if I'm gonna just find out what is my sampling time, it's gonna be half of this, right? In that case, it's from here to here, or maybe from here to here. Here also, I have the sampling time shorter, right? That's why I have more sampling at higher range of frequency, and it is giving me like trend of the signal behavior. What if I have more like frequency? At higher frequency, I will get more samples, for example, here, here, and here. Then if I have more samples, this one will be more accurate, right? This one will be more accurate, and I can understand the trend of this or the behavior of the captured digital input more clear. So in the third case, again, I have lower frequency. So my captured signal in here, it doesn't show any analog input at all, right? It's just something. So make sure we are not going to use anything less than 2F for our controlling application, especially for some applications such as automotive application, because we always must have some data from some sensor in minimum 2 times faster than the original signal change, but the maximum can be even up to 10 times, right? This is going to be the maximum, but the minimum should be at least 2 times or 2F, right? Anything less than 2F, like for example, what you are seeing in here, or what you are seeing in here, or maybe even 1.7, 1.4 or so, these are not going to give us any understanding about the behavior of the original signal or the analog input. That's why we want it to for sure be at least 2F or above until, let's say, 10F. This is what we are looking for designing a like converter. Now, I have discussed about like some theory exactly like this one to not to have less than 2F. This is what we call it Nyquist theorem, that says a periodic signal must be sampled at more than 2x the highest frequency component of like the thing. So this is going to be the sample frequency, right? This is going to be the sample frequency, and this is going to be the highest frequency component of the signal. This is how we are going to calculate it. So for real application, we want something around 10 FC, right? So now we have another challenge for choosing the best analog to digital converter for our application. So we should consider, we already said, we should consider the number of input, we should consider the resolution, for example, 8 bits or maybe 16 bits. And also now, the other challenge is this one, considering the frequency. We have to consider the frequency of analog to digital converter. So if the Nyquist rate is about 1 kilohertz, it is good for real application. And those with higher frequency, about 2 kilohertz, it is good. And anything like with higher frequency will be more expensive. Why? Because they are going to have a faster processor to do the method of the successive approximation that we have discussed it earlier. That's the reason to have those with higher frequency a little bit more expensive. Well, for example, probably you have Arduino at home or maybe for like other courses in the lab. And also we are using it for this lab as well. So the Arduino is having a maximum of 900 hertz. That is why it is not very expensive. So the resolution is not that much high. So it's not very expensive. Or maybe the temperature sensor that you have at home. Those are not very expensive because you don't have a very fast sampling. So they just take the sample with some maybe lower speed. Now, there is another example in here for you that you are asked to define the minimum sampling rate to avoid the signal aliasing for this analog signal, for these two analog signals. So how to define the minimum sampling rate. This is going to be something very easy. Let's go over it quickly. So this is going to be example 6. So we need to consider this two analog signal, which are given in here. So let's say the first one is going to be x of t is equal to 3 cos, this is going to be 100 pi, right? And the second one is given as x of t is equal to 3 cos 50 pi plus 10 sin 300 pi minus cos 100 pi. These are the samples or the analog signals that we have. Now, the sampling frequency fs should be at least twice of the highest frequency contained in the signal fc, and this is what we have learned just in here, right? So knowing that for signal 1, what do I have? Generally, you have to remember this one. Like, this is a general format, a cos 2 pi ft equals to what? Equals to 2pf. In this case, it is 100, right? So then how to calculate the f? It simply is (100 over 2), which is 50 hertz, right? Now, from Nyquist sampling theory, you have from the Nyquist theorem, what do you have? You have Fs must be at least 2 times Fc, which means in this case, your Fc must be bigger than 100 hertz, right? So the frequency is 50 hertz. So the sampling frequency of analog to digital must be at least 100 hertz to avoid signal aliasing. How about the second one? So this is for the first one. For the second one, you have already the like FC from here, you can tell. How to calculate the FC? It is going to be equal to Fs over 2. In this case, this is 50 over 2. It is going to be 25. So another sampling in here. In this case, it is going to be Fc equal to 300 over 2, which is 150. And you've got another one in here, right? In this case, it is going to be Fc is equal to 100 over 2, which is 50. So the signal has three frequencies as like 25, 150, and also 50 hertz. So the sampling frequency of the analog to digital converter must be at least 300, because this is the largest one. It must be at least 300 hertz to avoid the signal aliasing. So then from here, again, from Nyquist theory, what do you have? You have Fs bigger than 2 Fc. So Fs is bigger than F. How much is it? Is like 150, right? And from here, this guy should be bigger than 3 hertz, right? Right? It must be bigger than 300 hertz. So now you learn how to deal with those challenges, and finally, also today you learn how to find the proper like analog to digital converter in terms of frequency. Now let's look at the structure of the analog to digital converter. Usually what you see in this slide is like the register block diagram. This one is available for every other analog to digital converter as well. But this is the one that we have in the lab, which is the HCS12. So in the lab, this guy is having like 10 bits. And it can be configured as 8 bits. It has 8 analog input channel. And also it is accepting the differential voltage, which is equal to what we have discussed earlier, which is equal to V reference, reference low minus reference high. So it is accepting this one as well. And also, if you look at here, this guy is in here. These are the 8 channels that we have. So as I explained earlier, this switch is controlled by successive method of approximation, and it can switch between different inputs in here, right? So, and as soon as this one is closed, this capacitor is supposed to get charged, right? And also this unit in here is the sampling and hold unit. This guy is here, in here is the successive approximation, which is also 8 to 10 bits. And remember in the lab too, I said we use the 8 bit for our application in here, and 2 of them are like for other application, 2 of them are free. So any of the module we are using in the lab, they don't have a sense of time, and they are working based on a sequential work. So if I want my capacitor in here to be charged, let's say for a certain time, whatever, then of course I have to make sure that this switch is in here can remain closed for the same time. For example, if I want this one to be like 2 seconds, I have to be able to send the command to this switch to also be closed, because if the switch is closed, then I am going to receive some charge from the external like source to charge the capacitor. But without that, it doesn't have, without any clock, it doesn't have any sense of time, right? Also like other temperature sensor and so on, none of them, they can understand time. What do I need to have to do in here? There is an external crystal, which is this guy. I'm gonna have some crystal oscillator in the microcontroller. Some of these oscillators are built in, but those are not fast enough. But the external one, this is oscillator. Let me draw it like bigger for you. Right? So I am going to have, actually we do have this external like oscillator in the microcontroller to generate the clock signals for clocking the data in digital circuits, right? Because we want it to understand like time, and it doesn't understand if we don't have such a clock. So this is going to be generated using like electrical signal with a constant frequency. This is how this guy is working. If I have 16 megahertz in here, right, which is the natural frequency, then the main bus is half, right, which is let's say 8 megahertz. Then I need the scalar, which is this guy. Let me just make it bigger. Then I need the scalar to sample it up and down to convert the 8-bit, which is this guy, to convert the 8-bit to like signal. Now, this analog to digital is working in the range of 500 kilohertz, right, to 2 megahertz. Generally, this is a fast converter, right? So the faster case is 2 megahertz, and the lower case or the slower case is 500 kilohertz. Well, this is again what we practice in lab 2. Let us review them quickly. So we have control registers, as we discussed, to control the overall operation of the analog to digital converter. So the power is not initially on in the microcontroller. So what you need to do in case you are going to power it up, you have to just turn it on. So we have interrupt. We are going to discuss the interrupt next session to generate the interrupt in any case that you need to have it. And also there is external trigger, right? So also you have to wait for mode. This one is just holding the process for some time if you need to. And also you have first in, first out. So you have the conversion sequence length. What this one is doing, this is going to also you have the like control freeze mode. These are going to determine the total number of the conversion, right? This is going to tell you how many like conversion you need, as we have just calculated. And also you have the conversion clock frequency, right? You practice those one. And this is going to just give you a sense of time sampling. And also you can just adjust the resolution as well. That can be either 8-bit or 10-bit. And we have discussed to consider 8-bit for our application. Also the analog input channels that we have, also you can justify them, which means how do you want to write your binary value, either from left to right or from right to left. And also how many inputs you want, one or maybe multiple inputs. And of course the conversion type. These are what you have them for this microcontroller in the lab. So you have another register, which is the input enable register. This register, if your microcontroller has, let's say, 10 analog ports and you are not using them, it will give you the opportunity to convert those like analog to digital ports. Actually, you have to bypass the analog to digital converter, then you can just reuse those ports as like digital ports. And also you have the result register that can hold the result of the conversion, and this can store the captured analog into 2 8-bit result registers. Well, here you see the structure of the register. For example, ADPU, which is like bit 7 in here, is going to power up, as you can see it in here, and it is 0 by default. Again, if you wanted to just power it up, then you have to turn it 1, you have to switch it to 1. And you have bit 6, which is in this case AFFC, which is the fast flag clear. And what you practice in the lab, exactly, it was like this too. So for every analog to digital converter, we have similar data sheets, right? So that you have to check them carefully to program your microcontroller and choose the right bit for your code based on that data sheets. So you have like also other power down, which is going to be like bit 5, and we have already practiced this one in the lab. So I'm not going to repeat this like 2 slides because you already reviewed them and you don't need to remember them. Each time that you are going to program your microcontroller, you have to go back to the data sheet and find them from the data sheet. Now, also we have another analog to digital register, which is register 3. We have already completed register 2. This one is going to control the number of the conversion. So how many conversion do you need? We have already calculated this one mathematically, but this is how you can find also from the data sheet. Whatever you have in here, bits 6 to bit 3, these are all going to just look at the like conversion per second, per sequence, right? These are going to do the converting, like the number of the conversion for you. So if I have, let's say 0, 0, 0, 1, if I have all of them like this, what is going to happen? It make like 8 conversion for me. And how you know that? From the table. For example, if these are going to be all 0, 0, 0, and 0, this is going to do like 8 conversion for me. And if it is going to be 0, 0, 0, 1, it is going to do 1 conversion, and so on. For example, the one in here, which is 0, 1, 0, 0, 0, 1, 0, 0, is exactly this one, which is the default case, which is going to do 4 conversion, right? So if you have a signal which is like a smaller, right? So then it will do more conversion. It's like it will go like up to even 8 conversion for you for the same channel. So it means you have 8 variable for a single channel, and this is good. Why? Because it can just have the average of the 8 variable, and in this case it doesn't need to just evaluate 8 different number. It is just going to evaluate the average of them, which is going to just be used for high frequency noises in case you have some application with a lot of noises. So how about the other bits in here? These 3 bits in here are going to just be the first in, first out, like the first one. This is the first in, first out. And the other 2, you can just pause the code using this. Like, for example, at any point that you wanted to pause your code, you need to just use this 2 bits. Or if you wanted to interrupt the code, that we are going to discuss it soon, then you need to just use these 2. So You can stop also the conversion using these two like beats. And also, for example, if you have 0, 0, look at here, it will continue the conversion. If you have it like 1, 1, in this case, it is going to continue the conversion. But if this is 1, 1, it is going to freeze the conversion immediately or stop the conversion immediately. So if you have it 1, 0, what it is going to do, it is like finishing the like current conversion, and then it will stop it or freeze it. And also the case that it is 0, 1, it is going to reverse the conversion. So these are how these beats are working for you. Now, as we saw in the lab, we have also control register 4, and we did a lot of practice in this control register. So this is about the resolution, right? This is going to just show you the resolution. Each bit of this register is going to do something. In this case, for example, this bit is for resolution, and it can be set to either 8-bit resolution or 10-bit resolution. If it is 0, it is 10-bit. But if it is 1, it is going to be 8-bit resolution, right? Now, there are 2 more bits in here, right? These 2. These guys in here are the sampling like period for changing the sampling time based on this table. So you can use this table for that purpose. And also you have some other bits from bit 4 till bit 0, from here to here. These are all going to be for the pre-scale for the clock. So you need the external oscillator. Of course, that's available in the lab. So based on that, you can just use them for the clock. Now, here is how you can calculate the analog to digital clock. And also, the conversion frequency must be between, again, 500 kilohertz and 2 megahertz. This is what I have already discussed. So, for example, if I have the bus clock, let's say something like 8 megahertz, then I have to use the prescaler, and this prescaler, it can be any number. Look at here, we have already cited in the previous slide as well, +1 and then times 0.5. So this is how you can calculate the analog to digital clock. Now, let's look at the clock frequency structure and practice this one a little bit more later using some example. Well, as I mentioned, if this is, let's say, 8 megahertz, it will be delivered by the prescaler, right? And then this one will be set based on the application that we are looking for. And then it will be sent to the sampling right after here. It will be sent to the sampling in here. So this sampling in here is just 2 register, but as I mentioned earlier, it can be up to 16 register as well. So, and then in here, in this sampling circuit, remember we had a switch and a capacitor. So as soon as the switch is closed, the capacitor in here will start charging. And then what we are going to have in the next step is like this analogs like inputs. So now let's see how we can just calculate it. For example, this is going to be my initial sample, right? And this is going to be just 2 clocks. The final sample can be something between 2 to 16 clocks, and the conversion time, it is going to be the number of the bits, so it is going to be 8 or 10 bits. So if I'm gonna just consider the lowest one in here, for example, the initial sample is going to be, let's say 2, and then the final sample can be something between 2 to 16, right? And then the conversion time is going to be something between 8 or 10 bits. So then if I use only the lowest one, let's say this, like 3, then 2 plus 2 is 4, and 4 plus 8 is going to be 12 clock for the lowest one. If I am considering the highest one is going to be in here 10, 16, this is 26, and then by 2 it is going to be 28. So it means it will be 12 to 28 clock, right? To convert one value. This is what we need to convert one value in the HCS12 analog to digital register. Now, I'm gonna just solve another example in here for you to make that a little bit more clear on how to calculate that clock. So this is going to be example 7. And in this example, you are asked to look at here. The bus clock frequency is going to be 8 megahertz for the microcontroller in the lab. And then the analog to digital module work in the range of, as I mentioned, 500 kilohertz to 2 megahertz. You are going to choose the converter clock prescaler beats for PRS4 and PRS0, right? So the clock for the analog to digital has register like ATD, remember we used this in the lab, ATD CTL4, right? To scale down the main bus clock. And I just show you how is the structure of it. Let me just copy that one for you and bring it here. This is the structure of the register 4, remember? So in here, bit 4 to bit 0 will do the pre-scaling. Look at here, PRS, and so on. So these are all going to do the pre-scaling. So from the analog to digital clock, we just learned that the A to D clock is equal to the bus clock divided by the PRS plus 1 times 0.5. So as I mentioned, this prescaler can be different number based on the table that we had it in the previous slide. Now, for the faster conversion, again, I'm going to go back to this picture. I can bring also that one here for you. For the faster conversion, I'm going to use like 2, right? Exactly like what I did for the previous step. So that's why I'm going to just mention it. For the faster conversion, I'm going to use this one like 2 plus, also this is 2 to 16. In here also, I'm going to use 2 final sample time. And also this is going to be either 8-bit or 10-bit, since I'm going to have it like a shorter conversion or shorter, let's say, result, then I'm going to select the 8, right? So it is going to be 12 clock for the faster conversion. So it means it takes 12 clock to have one binary value from the conversion. How about the highest frequency? For the highest frequency of the analog to digital, that will be at 2 megahertz, like what you have it in from here. Then the pre-scalar, you can calculate it like this. The pre-scalar is going to be 8 megahertz over that 2 megahertz, right? Times 1 over 2 minus 1, which is equal to 1. What does this mean? This means the pre-scalar should be 0, 0, 0, 1, which is the sky, right in here. And you can find that one from the table as well. This one should be 0, 0, 0, 0, 1. This is how you can calculate the pre-scalar. Now, if the analog to digital works at 2 megahertz, the total conversion time, you can calculate it like this. Right? So you can say the 12 clock, we have already 12 clock, times the sampling time. What is the sampling time? 1 over the frequency, and frequency is 2 megahertz. Remember I said TS is 1 over FS. This is how I find this term in here. Then if you calculate this one, this is going to give you 6 milliseconds, which is something around 167 kilohertz. So the highest frequency is 167 kilohertz to convert 8-bit value, right? Now, remember we had the Nyquist theory. From that Nyquist theory, I can now simply say the 167 kilohertz over like 2 is going to be 88 kilohertz. What is this? This is the highest frequency. This is the highest frequency by this analog to digital. So I think we should stop it right in here, since the remaining slides are exactly what we have practiced during the lab time. Slide 23, it is going to be again another control register 5. We reviewed this one, how the structure of the register is and each bit is doing what. This is exactly what we practiced during the lab time. And also you saw that in the data sheet there is another table that you have to figure out, like the proper registers using that. This example 8 is also solved and the solution is published on Adlib. Stay happy, stay healthy, and I will see you next time.